If a western diamondback injects venom into you, it can damage tissue and sabotage the systems your body uses to stop bleeding. The snake, meanwhile, makes that same weapon inside its own head and carries it for life. You get one bad exposure, it gets a lifetime, so why are you the vulnerable one? The obvious answer is immunity. The snake makes the venom, so its body must simply be immune to it. That explanation is neat. Too neat. Rattlesnake venom isn't one chemical with one job. It's a mixture of proteins and enzymes that can damage tissue, interfere with bleeding control, and disrupt different systems in the body. So saying the snake is immune raises a harder question. Immune to what, exactly? Being resistant to one part of that mixture doesn't automatically explain the rest. Humans put warning labels on household cleaners. A rattlesnake carries biological weapons inside its head and goes about its day. So immunity isn't necessarily wrong. It's just too small an answer for a system this complicated. So the real question changes. Where is the venom and what has to protect the snake there? Inside the gland, the snake has one problem. If dangerous components escape into circulation, it has another. And as the venom itself changes over evolutionary time, the defenses can change with it. Each boundary creates a different problem. What stops the snake's own weapon at each point where the system could fail? Now break the containment. Start with the first boundary, the venom gland itself. That gland is not just a bag full of venom. It works more like a storage vault, a place built to hold dangerous chemistry without letting all of that chemistry run at full strength against the tissue around it. Studies of rattlesnake venom glands show that the venom is stored under acidic conditions. That matters because the lower pH suppresses the activity of some of the venom's destructive enzymes while they're sitting in the gland. The weapon is still dangerous. It has not been neutralized. The snake is storing it under conditions that make it safer to hold. So before the blood has to defend anything, the rattlesnake has already solved the first problem. Keep the venom where it belongs and keep part of its destructive chemistry under tighter control while it waits. Keep it contained. Now let that boundary fail. A dangerous venom protein reaches the snake's circulation. Here, the problem changes again. The snake does not need every part of the venom to become harmless. It needs ways to stop certain toxins from doing the jobs that make them dangerous. And Western diamondback blood already contains some of those defenses. Researchers found one blood protein that can latch onto a surprisingly broad range of the snake's own tissue-damaging venom enzymes. They call it FETUA3. The name matters a lot less than the job. Think of it as a molecular catcher. It is already circulating in the blood. When certain venom enzymes show up, this protein can bind to them and sharply reduce their ability to attack the proteins they normally target. The catcher does not erase the toxin. It interferes with the toxin's ability to do its job. In laboratory tests, this one catcher bound roughly 20 different venom enzymes from the Western diamondback. That is a very different situation from yours. Your body did not evolve with this particular defense already waiting for rattlesnake venom. And that finally explains the contrast we started with. A rattlesnake can survive exposures to venom that could devastate you because its body has protections yours does not. It manages the venom while it is stored, and if major venom enzymes reach its circulation, natural blockers are already there to intercept them. The blood fights back. But that does not make venomous snakes invulnerable. Fatal self-envenomation has been documented in another venomous species, a brown tree snake. That case does not tell us how vulnerable a Western diamondback is. It tells us something narrower and more important. Self-resistance is real, but snakes are immune to venom was never a safe rule. And even when resistance works, the venom itself doesn't stay frozen in time. Venom proteins diversify over evolutionary time, and the parts of the venom doing the most work can change. The defenses can change with them. Researchers found that pattern in the Western diamondback. In some related pit vipers, one member of this defensive protein family had been identified as the main blocker. In the Western diamondback, a different member had taken over the major role. You do not need the family tree to see what happened. The weapon changed, the safety system changed with it. Defense evolves too, and that major blocker was not alone. Western diamondback's blood carries several related blockers, which raises a much better question. If one protein could catch so many venom enzymes, what were the others doing? In 2026, researchers tested them together. They studied 4 related toxin-blocking proteins from rattlesnake blood. Some individual proteins could suppress important effects of the venom on their own, but when the researchers asked the harder question, could one protein by itself stop the venom from being lethal, the protection was incomplete. Then they combined them. Certain combinations covered gaps the individual proteins left open. In preclinical mouse experiments, those combinations fully neutralized the lethal effect of rattlesnake venom. The strongest combination was roughly 10 times more potent than the commercial antivenom comparator used in that study by protein amount. And the effect did not stop with one rattlesnake. Those natural blockers also neutralized lethal effects from several other evolutionarily distant vipers. That does not mean scientists now have a human antivenom that is 10 times better. These were preclinical experiments. The proteins do not neutralize every toxin in every venom, and a result in mice is not the same thing as a proven treatment in people. What the experiment showed was more interesting. One blocker could do a lot. The combination could do more. At that point, the biology was no longer just a curiosity. It was starting to look like a blueprint. And the reason that matters goes far beyond one rattlesnake. Western diamondbacks are an American story. Snakebite isn't. In India, a nationally representative study estimated about 1.2 million snakebite deaths between 2000 and 2019, roughly 58,000 a year. Most occurred in rural areas. And here is the frustrating part. Good antivenom already saves lives. The challenge is getting the right antivenoms, the right patient quickly enough, against venoms that can vary dramatically from one species and even one region to another. That is why researchers are still looking for defenses that could be broader, more consistent, and easier to produce. For more than a century, the basic recipe for antivenom has been remarkably consistent. Expose a horse or sheep to snake venom, let its immune system make antibodies, purify those antibodies from the animal's plasma, then use them to treat the patient. It works. But the 2026 study starts somewhere else. Instead of asking another animal to make antibodies against the venom, researchers started with defensive proteins that rattlesnakes already carry in their own blood. Those proteins can be produced in the lab, selected deliberately, and combined according to which toxins they block. That is the real reversal. The snake is no longer just the source of the venom, it is also a source of potential antivenom components. And because these are defined proteins, researchers can test exactly which combinations cover which toxins, then ask whether those combinations could become recombinant antivenoms that are broader, more consistent, and easier to manufacture. The 2026 study tackled one major family of venom toxins. Researchers are now pushing the same strategy toward others, and that's the real test. If the approach keeps expanding, its value will not be one miracle protein. It will be a new way to design antivenom piece by piece around known toxin targets. That still leaves one enormous problem untouched. Treatment has to reach the patient in time. A better antivenom cannot help someone who cannot get to it. But this approach could change what that treatment is made of, moving from a variable mixture of animal-derived antibodies toward precisely defined defensive proteins that can be manufactured and combined deliberately. For a disease that still kills tens of thousands of people every year, that matters. The next breakthrough may not come from finding a more powerful weapon against venom. Part of the next defense may already be circulating in the animal that makes it.